Hello friends, welcome to my YouTube channel Maths DNA from origin to infinity. Before we begin, let me ask you a question. I am not alive, but I grow. I don't have lungs, but I need air. Who am I? Think about it and comment your answer below in the comment box. This is my 12th lecture on real analysis, and in this lecture we will discuss about series. We will also discuss about definition of a series, finite and infinite series, sequence of partial sums, convergent series, divergent series, oscillatory series, and conditions for convergence with some examples. So let us begin. Now what do we mean by a series? Now let an be a sequence of real numbers. Then a1 plus a2 plus a3 up to an is called series, which simply means adding the terms of the sequence. Then we have finite and infinite series. Now it is but understood that what do we mean by a finite and infinite series. If the terms are finite, it is called finite series, and if the terms are infinite, it is called infinite series. Like summation I running from 1 to n ai. Here n is finite, so the sum and the series is finite. Similarly, summation I running from 1 to infinity ai. Here the terms are infinite, so the series is infinite. Simple enough. Then we have sequence of partial sum. By the name we can understand that in this we will be adding terms partially, that is one by one. Suppose summation an is an infinite series, then we define Sn as follows. S1 is equals to a1, S2 is equals to a1 plus a2, adding two terms. S3 is equals to a1 plus a2 plus a3, adding three terms of the sequence. And so on, we get Sn is equals to a1 plus a2 up to an. Then the sequence Sn is called the sequence of partial sum of the series an. Now we have convergent series. A series summation an is said to be convergent if the sequence Sn of partial sums of summation an is convergent, and if limit n tends to infinity Sn is equals to s. Then S is called the sum of the series summation n, and we write it as S is equals to summation n running from 1 to infinity an, which means that for a series to be convergent, the sequence of its partial sum must be convergent. Then divergent series. The series summation an is said to be divergent if the sequence of Sn of partial sums of an is divergent. And oscillatory series. The series an is said to be oscillatory if the sequence Sn of partial sums of an oscillates. We will understand this more clearly with the help of some examples. Then we have necessary condition for the convergence of a series. If the series summation an converge, then limit n tends to infinity an is equals to 0. But we need to note it down that the converse of the above theorem need not be true, which means we have a counter example for the above theorem, that is, take summation 1 by n, then limit n tends to infinity 1 by n is equals to 0, but summation 1 by n is not convergent. This is a very important example. We also need to note down that if limit n tends to infinity an is not equals to 0, then summation n cannot converge. Now let us discuss some examples and understand the concepts more clearly. Example 1. Check whether the series summation minus 1 raised to n is oscillatory or not. We observe that S1 is equals to minus 1, S2 is equals to minus 1 plus 1, which is equals to 0. S3 is equals to minus 1 plus 1 minus 1 is equals to minus 1, and so on. So we get Sn is equals to minus 1 0 minus 1, which definitely oscillates, and therefore the given series is oscillatory. Example 2. Check whether the series summation minus 1 raised to n into n is convergent. Now we observe that S1 is equals to minus 1, S2 is equals to minus 1 plus 2, which is equals to 1. S3 is equals to minus 1 plus 2 minus 3, which is equals to minus 2, and so on, which gives us Sn equals to minus 1, 1, minus 2, and so on. Now which is not bounded. Therefore, Sn is not convergent, and therefore summation minus 1 raised to n into n is also not convergent. Now example 3. Check whether the series summation n upon n plus 1 convergent or not. We have Sn is equals to n upon n plus 1. Now taking n common from the numerator and denominator, we get Sn is equals to 1 upon 1 plus 1 by n. Now applying the limit, as limit n tends to infinity, Sn is equals to limit n tends to infinity 1 upon 1 plus 1 by n, which is equals to 1, which is not equals to 0. As limit n tends to infinity, Sn is not equals to 0, the given series is not convergent. Thank you, and get the best material for preparation by just one click. The link is given below in the description. Also, check out other 30+ videos on my channel.